The falling velocity of a particle is a very important parameter in sediment transport. What you see in your packet is that the falling velocity equals this huge, maybe complex equation right here. But after this video, you will learn where this equation came from. As we know, the falling velocity of a particle will be constant when the driving forces of the particle equals the forces resisting the motion in the particle. Setting these two forces equal to 0, we get this simple term right here. Now, this would make complete sense and would be easy for all of us if the drag coefficient would be constant, but rather it is not. Experiments have shown that the drag coefficient is 1.4 plus 36 over the Reynolds number, and the Reynolds number is dependent on the falling velocity of the particle. So we now have the falling velocity of the particle on both sides of the equation. So the first thing to solve for it would be to square the falling velocity over here. We still have our 4/3 up here, original term, and this is our drag coefficient. We now will multiply times the denominator, and we get this term right here, 1.4 times omega squared plus 36 nu over d omega equals the term we have on the right. We quickly notice that this is a quadratic equation, and recall the quadratic formula is this right here, negative b plus minus square root of b squared minus 4ac divided by 2a. Basically what we need is to figure out our a, our b, and our c. In our case, our a is 1.4, our b is 36 nu over d, and our c is negative 4/3 s minus 1 g times d. Plugging this into the equation, we have our b, plus we are only interested on the positive root of our equation. It's the only one with physical significance. The square root of b squared minus 4ac divided by 2a, which is 2.8. Further simplifying this would give us what we saw at the beginning. This is the falling velocity of a particle in a channel. I hope you now understand where this came from, and you are able to derive this yourself.